All right, I'm going to make this sound like the beginning of an official meeting. It's an official meeting, so I want
It's
it
a
to sound
meeting.
like what?
Yeah,
It's a meeting. It's a meeting of the Chicago, Illinois, and beyond quantum meetup group. And the speaker today is Peter Selinger. He's a professor of mathematics at Dalhousie University. His research is on the semantics of programming languages, quantum circuit theory, combinatorial game theory, type theory, category theory, among other things. I'm excited
right.
that you're talking because I'm interested in both quantum computing and functional programming. I'm teaching Haskell right now and loving it. So, with that, I'm going to invite everybody to um, chime in because Peter says he would prefer an interactive discussion. And um, Peter, if you will start sharing your screen and unsharing your hoodie.
Okay.
There we
Why did
go.
I do that? Yeah, I was trying to install Zoom on my other device, but I think I'm going to give up on that.
That's
So
always going to lead to trouble.
yeah, that's always trouble. All right. Participants can now see my screen. That is awesome. Yeah, so Halifax, in case you don't know, is in Canada. It's in Nova Scotia, which is basically near Maine for the Americans, right? So it's roughly where can you see my cursor there?
Yes, indeed.
I think that's like where the Titanic sank when it was like going to New York down here. And so Halifax was the closest port. And it's, people usually think it's near the North Pole, but it's actually not. It's quite temperate here. And like I said, think near Boston, basically. There's Boston down there. And the university is called Dalhousie University. It's named after, I think, the fifth Earl of Dalhousie, who was the only member of his family who called himself Dalhousie and not Dalhousie. So there's a Dalhousie clan in Scotland. And this one person decided that he's called Dalhousie. So that's what the university is called. It's confusing. It rhymes the lousy university, easy to remember.
I looked it up before the meeting and I saw conflicting opinions about how to pronounce it.
Exactly, because in Scotland they're all called Dalhousie, and there's a Dalhousie Street in Ottawa and so on. It's just this one member of the Dalhousie clan who pronounced his name differently. But that's the one we're named after. So the Quipper quantum programming language. It's something we did now almost, I'm thinking, almost 15 years ago, 13 years ago, something like that, which was at a time when no one else was interested in quantum programming yet. You may remember this. Like 15, 20 years ago, all the quantum research was algorithms and complexity, and we simply weren't close enough to building any quantum computers that most people would care about programming. But that's very different now, right? Because all these NISQ devices and so on, and people are programming them a lot, and there's all kinds of different toolkits and languages and libraries and things. So Quipper is one of the oldest of these, and for some reason you guys wanted me to talk about Quipper, so I'll tell you all about it. So Quipper is a high-level programming language for quantum computation. By high level, I mean there's usually a pretty big gap between how a quantum algorithm is described in a research paper and the actual gate-by-gate circuit that you would have to construct at the end of the day, right? No research paper says, oh, take 50 qubits. Now first apply a control NOT gate to these 2 qubits, then apply a Hadamard gate, right? It's not like that. The description is usually high level. It might say something like, such and such problem is well known to have a classical solution that runs in time O of n cubed. Using standard techniques, we can make a classical circuit, of this size. And then using other standard techniques, we translate that into a quantum circuit. Then we apply 3 steps of trauterization and some kind of amplitude amplification. So you apply sort of high level concepts. You don't actually describe the circuit. You give reasons why such a circuit exists. And we would like a programming language, or at least that was the goal of Quipper, where you could describe the quantum algorithm, you could program it at a level that followed as closely as possible this kind of high-level description. So of course, in Quipper, it's possible to program gate by gate, but it's also possible to do sort of large picture things, like take a circuit and then transform it in some way, make it reversible, make it, I don't know, apply the error correction or iterate it or whatever. So for that reason, Quipper, so any previous quantum programming languages that we had, they were all sort of designed for the QRAM model, where you basically, the minute you execute an instruction, it immediately gets executed on the quantum computer. But Quipper is a circuit description language. You can construct a whole circuit and sort of store it in a variable and then operate on the circuit, right? So for example, first you construct a classical circuit, then you make it reversible, then you make it quantum, then you replace certain gates, then you do optimization, then you apply, I don't know, some technique like a quantum Fourier transform or whatever. So here's a list of some of the Quipper developers and algorithm implementers. Well, what did we want? I already mentioned we wanted Quipper to be high level, also general purpose. So we should be able to program any kind of quantum algorithm, and there's many different kinds, right? Realistic. So we don't want a language to be limited by the size. Okay, if we need to program a circuit having 30 trillion gates, then we want to be able to do that in Quipper. So we don't just want sort of toy examples, but actually hopefully implement algorithms at fairly reasonable problem sizes. Now I should say we didn't have a quantum computer, and we still don't. Quipper is not designed for noisy intermediate scale quantum computing, right? Quipper is a programming language that is designed for the future. So when we actually have universal error corrected, idealized quantum computers. So Quipper is not about you have 100 noisy qubits and now you try to, get the maximum sort of thing you can out of those. Quipper is designed for large algorithms, maybe with thousands of logical qubits or whatever. So maybe realistic should be in quotation marks, because this is not currently realistic, right? But we're hoping that maybe one day it will be extensible. So you can write Quipper libraries. There's a lot of Quipper libraries already that do different kinds of things. Concise. So one problem with some programming languages is that it takes 1,000 lines of code to do something really simple. Especially object-oriented programming is a little bit like that sometimes. You have to write a lot of template stuff, classes, and a lot of helper stuff before your program does something interesting. So conciseness is nice. It's nice if we can do something interesting with 5 lines of code, right? It should still, concise doesn't just mean short, right? It means as short as it should be to kind of still be readable. Safe is nice. We like type-safe programming languages. It's great if many errors get caught at compile time rather than at runtime, because it's very disappointing when you just generated 30 trillion gates, and when you generate the next gate, you get some kind of error. So that's costly, and certainly you don't want to discover, well, because you're going to run your programs one day on a quantum computer, they're not particularly easy to debug, because the computer might run for 1.5 years and then give you the wrong answer. And so it's nice if we have a language that we can reason about, so we can maybe do something like formal verification before we run the program. And scalable, as I mentioned. We mostly used, since we don't have the quantum computers yet, we mostly use Quipper for resource estimates. People who invest money in quantum computing usually want to know 2 things. What is it going to do for me, and how much is it going to cost? So, you can say, oh, quantum computing will be great for chemical simulations or whatever, but you actually want to know, how much energy is this computation going to consume, and how many gates, and how long is it going to take in terms of time. So for resource estimates, we've done that for, like, let's say on the order of trillions of gates. We've been able to simulate or count with Quipper, so it's fairly scalable that way. All right. So we made some design choices, and you can question these. Maybe you would make the choices differently, right? Different people like different kinds of things, but the choices that we made for Quipper, first one is Quipper is a functional programming language. Most people, I've had people complain and say, how can I teach Quipper to my students because all they know is Python? Then I have, well, what can I say, right? You're teaching your students. So Quipper is a functional programming language, which is not like Python. Most programming languages that people know are imperative, which means every data structure is always stored in a variable, and the whole program operates by updating variables. Okay, for example, if you have an array of something and another array of something, and you want to apply a function f to these, you have a loop. So you let I go from 1 to n-1, and you do something. In functional programming languages, I don't know how familiar everyone is. Examples are Haskell or ML or Lisp. You don't so much talk about what the program does, but you talk about expressions. So you talk about what things are. And usually your data is still stored in variables, but they don't get updated. Rather, we apply combinators to data to compute new data. So when you want to apply the function f to a pair of lists, you would typically have some combinator like zip, which works like a zipper. And then you get C, which is a new data structure. So it works quite differently, and it uses a lot of garbage collection because if you don't modify your data in place, you constantly have to generate new copies of data, and old copies will become obsolete. But that works actually very efficiently with modern sort of garbage collectors and things. And the advantage is that functional programs are much easier to get correct. So the ratio of time spent programming and time spent debugging is much higher in favor of programming. And then you have such properties as type safety and correctness and also modularity. It's much easier to understand what a program does if it doesn't update like a random variable that you have to document, right? Anyway, that's a design choice that we made. And the second choice that we made is that Quipper is an embedded language. So we didn't want to, at first, generate a whole new programming language with its own syntax and parser and compiler and all the tools that go with that. We just wanted to leverage all the tools that exist for some existing language. So an embedded language is a way to do that. It's using Haskell as the host language, and then reuses a lot of these features. And the trade-off is that certain features of the host language are not always a perfect match for the embedded language. But the good thing is that it works really well and is scalable, and we already have all the tools for it. So what is an embedded language? I mean, I guess the one sort of point of view is that an embedded language is just a fancy name for a bunch of libraries, which is in some sense true. But usually when we speak of an embedded language, it has some particular data types that represent the embedded programs. There's some kind of libraries of primitive programs and combinators, some run functions to execute the programs, and an idiom, which is how you're supposed to write the program. Because in some sense, if your language is embedded in Haskell, every valid Haskell program will automatically be a valid Quipper program. But then there's a certain idiom for how you're supposed to write the Quipper programs. And I will show you some examples of these idioms in a second. Haskell is a very well-developed functional programming language, support for higher order functions, polymorphic functions, overloaded functions. It has many libraries already that can do lots of standard things. And it's strongly typed, which means that in Haskell, there's a whole class of runtime errors that cannot happen. They would all be caught at compile time. So there's some errors that do happen, like errors that are related to the unavailability of resources. Like if you run out of memory, for example, that's not something you can catch at compile time. But there are many other kind of errors, like typing errors, that really, in a strongly typed language, the guarantee is that you will never get a type error at runtime, right? All your type errors will be caught at compile time. That makes it relatively easy to write correct programs, or rather to write incorrect programs and then note that immediately and fix the program. So one thing that Haskell doesn't have is linear types, and those would be useful in quantum programming because you can't really duplicate the quantum data, which is one kind of error that Haskell unfortunately doesn't catch. So Quipper is not quite type safe, but it inherits some of that from Haskell. The third design choice is this sort of circuits that Quipper generates. Unfortunately, this is not really standard. Like when you generate quantum circuits, for example, well, it's something I already mentioned. When you take a description of a quantum algorithm from a research paper, it has these high-level things, construct this circuit, then do this to it, then do that to it. And you end up spending most of your time constructing the circuit. You spend very little time actually running the circuit, or maybe, or that's not what the hard part usually is. And so therefore, Quipper uses circuits as first-class objects. So you can store circuits in memory, and you can operate on them. You can transform them in all kinds of ways. So we have manipulations at the gate level. Certainly you can say something like apply a Hadamard gate to qubit X, but we also have a lot of manipulations at the circuit level, reversing, iteration, all kinds of support for classical oracles, ancilla management, and whole circuit optimization. So let me just mention, so because we have this, because Quipper is a circuit generation language or a circuit description language, it shares some of the features that hardware description languages have. It turns out that there's sort of three distinct times in Quipper programming. There's compile time, so you've wrote your program, it's source code, you're compiling it. And then there's two different kinds of runtime. There's circuit generation time, which runs on the classical computer, right? You run your Quipper program, and in theory, it outputs, a very large circuit, basically a list of gates. And then when you have the circuit, in principle, you take it over to your quantum computer and you run it there, which is circuit execution time, okay? So that's like a batch model of operation where you construct the circuit and then you run the circuit. There are many quantum algorithms that actually can work in a batch mode of operations like that, and there are others that can't. So there are some quantum algorithms that require, for example, after you run the circuit, you make a measurement, then you might make some modifications to your state based on the outcome of the previous measurement, right? So like sieving algorithms are like that, or any kind of iterative refinement algorithms. But let's say as a first approximation, we have these two distinct runtimes, and then this is raises certain kind of issues from a programming language point of view, because some values will be known at circuit generation time, and other values, typically quantum states or outcomes of measurements, will only be known at circuit execution time. So any value that's known at circuit generation time, we call a parameter. That could be, for example, in Shor's algorithm, a parameter would be the integer that you would like to factor, okay? That's an input to the algorithm. It's classically known. You know it before you even construct the circuit, right? You can basically optimize your circuit for the particular integer that you would like to factor. And then any kind of value that's known at circuit execution time, we call that a state, okay? Like this would be, for example, the quantum state during the Fourier transform or whatever. And so even in the programming language, we have to distinguish between parameters and states. They're both stored in variables, but some of them are not going to be known at the same time as the others.
Peter, can I
Another,
interrupt for a sec? We've got a question from Neil.
yeah,
Raise his hand. Neil, do you want to open up your mic and ask?
yes, please. Let me see if I can. What happened here? Where's Neil? Oh, I see. Zoom went and hid it.
Neil is unmuted. Neil, can you? But now Neil is muted. Hello, Neil.
I can't see much.
Okay, I guess we'll put that on hold for a minute. I have a couple of questions while we're
Okay, go ahead.
starting here. One of them is you mentioned that Quipper is 15 years old. Is it being maintained?
Barely. It's we haven't done very much with it in some time. Every once in a while I have to update it just so that it works with current versions of Haskell or whatever. So it still works. But honestly, we haven't really extended it much. It was already pretty good, 15 years ago, and I'll show you some of the algorithms. So it's, yeah, I wish we had more time to work on it really, but we've used it more recently than 15 years ago, but we haven't actually extended the language itself since then.
And as a fellow professor, I have this question: do you teach it?
I teach in a math department, so we don't really have a lot of hands-on quantum computing courses. So I haven't actually taught quantum computing in many years, so I would have to say no. I'm not currently teaching it.
Okay.
Yeah, but however, I've had people have been teaching it. Like my postdoc was, he's now at a different university. He's just now teaching a quantum computing course using Quipper. So, and I've seen it being, used in teaching in other universities.
Right.
That can work.
We've got.
But usually you have to teach people functional programming first, because
that would be a heavy lift.
Yeah,
I taught quantum and functional programming, but never together.
Yeah, right, exactly.
So we have Neil's question here. It says, my question related to the zipper example, where there was a zipping function followed by F, A, B, and what is F, he says.
So F was the function that we want, sorry, for some reason I'm in Acrobat Reader, but right click doesn't work. Oh, that's because I'm in full screen mode. F is, okay, I can't highlight while I'm in full screen mode. F is the function. So I have a list, let's say I have a list of numbers or an array of numbers A and another array of numbers B, and I want to make a third array of numbers where in the ith component, it, let's say, contains the sum of the numbers or the product or something. So F is whatever function you want to apply, right? Here, both in the functional and in the imperative program. So it's the function, some function that you want to apply. Could be addition, right, or multiplication.
Neil, does that answer your question? In the meantime, could you clarify what you mean by linear type that Haskell doesn't have?
I think we'll get to that.
Okay.
It's all very high level right now. I want to basically do a demo, but first I have to give you some of the design principles so that you know what I'm actually demoing, right? So we'll get back to the linear question in a bit. Okay?
Yes.
So where was I? Right, the final, I hope this is the final design choice. I don't actually remember, but Quipper circuit model. So a lot of toolkits that generate quantum circuits don't have a way to mark the qubits that are not currently being used. So you just have some ancillas and you sort of assume they're always there. So in this quantum circuit, we start 2 ancillas in state 0, then we do something and we uncompute the ancillas. And now from here to here, that qubit is actually equal to 0 because I'm finished using that ancilla, right? And then I need a new ancilla. I take it from the ancilla pool. But that's bad because when you're not using a qubit, then you don't need to error correct it the whole time, right? You don't want your entire storage to be full of idling qubits that you're error correcting. So everywhere the qubit is red, it's known to be not used. And then in fact, when you take ancillas from a pool, you don't even care which ancilla you take, as long as it's initialized to 0, right? You could use the second one instead of the first one or whatever. So what we do in Quipper is we annotate. It's a simple thing, but it's useful. We annotate not just when the scope of an ancilla starts, but also when it ends. And we put an annotation in saying that we, the programmer, are basically promising that this ancilla has been reset to 0. Okay, you can check that at runtime if you want by measuring it and then raising. It's like an assert in a program, right? There would be an error if it's not actually equal to 0. But most of the time, it's something the programmer already knows, because you know that you've used an ancilla and that you've uncomputed it. And it means that the volume that needs to be error corrected is just all the qubits that are currently in use. And then as you go through further tools of your tool chain, maybe some circuit level optimization, you add error correction, you add, you decompose to a different gate set or whatever, you can carry those assertions forward. So I think that's useful. And also we have both classical and quantum bits in our circuits, because even though the programming language is classical, there's also some classical information that will be known at circuit runtime. Like when you do a measurement, right? When you do a measurement, the output is a bit, but it's still in the circuit. So it's still a state. It's not a parameter, right? Because you only know it at circuit runtime. And then we have something called dynamic lifting, which is when you basically stop the quantum computer and say, okay, now I have these classical bits, I'm going to give them back to my very slow classical computer and then do some arbitrary classical computation. So for some algorithms, it's necessary to switch back and forth between these runtimes, but there are also many where it isn't. Okay, so that's my spiel, all the different background information here. And we can get rid of this. I can probably make this larger. And I just want to give you some examples for how you actually program in Quipper. So let's make a file called example.hs. Okay. So Quipper. First, it's an embedded language. So .hs is the standard extension for Haskell programs. We didn't sort of bother inventing a new extension for Quipper programs, but in order for it to become a Quipper program, the very first thing you say is import Quipper, and that should basically work now. So if I go there, wherever it was, I can run the Quipper interpreter on this file, and it just loaded the file. Okay, so now let's do something. Maybe the first example I should give is something like, well, I said there are all these high-level operations that you can use in programs, but maybe the very first thing we should do is just show you a low-level thing, right? Like at some point you have to program with gates, okay, before you do anything else. So in Quipper, like in Haskell, every function has a type, and we could start with something. We will program a circuit that, inputs 1 qubit and outputs 1 qubit. Okay, so here qubit is just a type of qubits, and circ, you can think of circ as a subscript on this arrow here, which just says this is not just any function from qubits to qubits, but it's a particular kind of function from qubits to qubits, namely one that's given by, that's actually a circuit. Okay. So read the arrow as a function type, like in math, right? When you say the function f goes from the set A to the set B, you write f colon A arrow B, and it's exactly the same notation here, except for some reason there's a double colon. So it's going to be a circuit that inputs 1 qubit and outputs 1 qubit. So then we input the qubit here. So we call it something like A, and then we can apply some gates to it. So maybe apply a Hadamard gate to it, and then well, there's not too many gates you can apply to a single qubit, I'm guessing. You could apply a NOT gate to it, and then return the qubit again. Okay, that's a very imperative style sort of program here. So let's see if that compiles. No, it doesn't. Couldn't match expected. Holy,
Do?
well, what is going on here?
Do?
Did I forget? I forgot a do, sorry. See, most errors get caught at compile time, which is great. And now I have to do something. I mean, I could check now what the type of example one is, but of course I can't really run this function. I would have to apply it to a qubit, and I'm on a classical computer, so I don't really have a qubit. But we have some things, and one of the things that you could do is you could ask for the circuit to be printed. There's various different formats that it could be printed to, but one of the formats that it could be printed to is called preview. And so we wrote this wonderful previewer for quantum circuits, and it's actually Acrobat Reader. So it just generates a PDF of the circuit and then shows it to you. So this is not super exciting, but it's just a single qubit. You apply some gates, right? So that's the gate, the gate level paradigm. Let's do something maybe slightly more interesting, only marginally more interesting. Okay, this time I'm going to input 2 qubits and output 2 qubits. So I input 2 qubits A and B, and maybe now I do a Hadamard on the first one, and then I could apply a NOT gate to the second one, and I could make it controlled by the first qubit. So we have this in the embedded language, we have this controlled keyword, which does exactly what you would think. You make a gate controlled by another qubit. Okay, and there's all kinds of things you could do. There's a syntax for you could make it a black dot or a white dot, or have it controlled by a whole list of qubits and other things. Then we could also have a Hadamard that's controlled, by B, for example, and then another controlled NOT gate again, and eventually return qubits. Okay, let's just see what that would look like. Reload, print example 2. Okay, it's like a little circuit. Okay, so far so good. Now, but that's not very high level, right? You could do that in assembly language. So let's do something a little bit more interesting. I want to write an adder. So for example, it's not interesting if we're just describing a circuit on 2 qubits, or even if it's 100 qubits, right? What you want in a program, not to write a program that generates one circuit. Rather, you want to write a program that generates a family of circuits. For example, Fourier transform, you might want to do it on n qubits, and you maybe don't know what n is, or don't care what n is at the time you. If you implement Shor's algorithm, you want to factor some integer, but that integer is a parameter to the algorithm, right? And when you have a parameter to the algorithm, what it means is you're actually generating a family of circuits, one for each integer, right? And you have to pick out which member of the family you want. So the simplest example I can think of for that is an adder where you could add 2 quantum integers, n qubit quantum integers. So first we're going to write or even, let's not even do adding, let's just do the Boolean AND of a bunch of qubits. That's even simpler. So my first circuit that I'm going to write, it's going to input 2 qubits and then use a controlled NOT and an ancilla, basically to prepare another qubit in the state that is the Boolean AND of the states of the 2 qubits. So how do we do this? I will initialize a new qubit. So this is an ancilla that gets initialized in the state 0. False is here the same as 0. Then I would negate it. I would negate the new qubit if the other 2 qubits are both 1. So I can control it if I control an operation by a list of qubits, it just puts the control on all of the elements of the list. So that's another simple circuit. Let's go look at it. Reload. It's a very simple circuit, but it just illustrates a few things. First, my program does have 2 inputs, and these are the 2 inputs here. But it nominally has 1 output, but there's actually 3 outputs in the circuit. That's because the other 2 outputs have become garbage now, right? Like I would later have to uncompute something to get rid of these other 2 outputs. So of course you can't have a quantum circuit, you can't have a unitary circuit that inputs 2 qubits and outputs just 1. But basically what we're saying is we only care about this qubit here, and the other two, we're basically going to forget them. Like there's some temporary garbage that that we need to collect that later, like I said, by uncomputing. But so this is a simple AND gate. And by the way, I am pretty sure I can put, when you write a large circuit, it can be a bit difficult to see what's what. Like, for example, you might want to see, was this the A and this the B, or was it the other way around? Which one of, if I have 50 outputs here, I might quite like to know which one of them actually is C. And I have, let me just see. Sorry, where did Quipper go? Yeah, so I can put a label in, and let me just illustrate how to do that. It's not a big deal, but it's just a convenience, okay? When you have a large circuit, it can actually be kind of hard to read. So what I'm saying is I have the pair of qubits A and B, and I want to give them a pair of strings as the labels in this output here. This is a pretty useful feature for debugging sometimes. So now when I look at the circuit, it'll actually say, oh, that's the A, that's the B, and that's the C. You can see what that is. And you can also put comments in, which is also useful. You could say something like enter AND gate and exit AND gate. And then when you read a large circuit, you can more easily find your way around it. Okay, but like I said, that's not it's more like it's a feature. When you have circuits with several hundred gates or tens of thousands of gates, that's actually quite useful. What? Does someone have a question or a comment?
What?
I can't hear you guys. I hear individual syllables, but
Ron, I saw Ron's tile light up.
Sorry, no, I did not have a question. I
okay, no problem.
Dropped something on the floor. Let me mute myself.
That is no problem. All right, now we have this little very primitive AND together two qubits, like as in a classical circuit, right? And now I want to write my first parameterized program. And what this is going to do is input a list of qubits, okay, and output a single qubit. And the thing is that the list is of arbitrary length, right? So I could apply this to 100 qubits or to 2, or maybe just even to 1. And so the length of the list is a parameter here because it's going to be known at circuit. But then the actual qubits in the list are state, because the actual state of the qubits won't be known until circuit execution time, right? So if the list is empty, I should just return a new ancilla that's initialized to true, because the AND of 0 bits is just true or 1. And then if the list is, I'm going to make a special case in case the list is a singleton, because in that case I don't have to apply any gates. The AND of a single thing is just that same thing. And then if the list is longer, it has a head and a tail. And like it would be normal in functional programming, you just program it recursively. So first we're going to take the AND of the rest of the list. And then we're going to take the AND of that thing, of the head and the thing we just computed. And then we return the new qubit. Okay, so let's try that out. And now if I want to view it, I'm going to get an error. Okay, and the reason I'm getting an error is this, like I just said, this program is actually a family of quantum circuits, right? For each length of the input list, I get a different circuit. And of course, when I ask Quipper to print the circuit, you're not going to know which member of the family it should print. And that's why this function is going to fail, because the print simple function only works for circuits that are not families, like if there's just a single circuit. So when I want to print something that's a family, I have to use print generic instead, and then I have to give a sort of a dummy argument For example, I can give it a list of 5 qubits, just five dummy arguments that are called qubit. And now I'm picking out a particular member of this family to print. And it's not super exciting. And in fact, I'm going to take the labels and the comments out because they make the circuit just look much larger than is probably necessary. You get something like this. It's just recursively defined, right? So it's even not the smartest possible circuit for doing an AND, but it just shows how you do a family of stuff. Like I could apply this to 100 qubits now. When I use 100 of them, I'm not going to type a list of 100 qubits, but I just use the replicate combinator, which just makes a list of 100 things, and you get, a fairly large circuit, which makes sense. Large, but not particularly interesting, right? It's just a bunch of control NOT gates. So now we have some circuits, that we can work with. And now we would like to do high level things with the circuits, right? That would be nice. For example, I have a lot of garbage here that I haven't uncomputed. And let's see. So let's make a reverse. My circuit is not reversible, right? We have to make a reversible version of it. And when you make a circuit reversible, it's going to produce, it's going to have some input and then an extra qubit where the output gets copied. And then because it's reversible, you also return all the inputs and you return the output. So this circuit, the reversible circuit, is going to input a list of qubits that I want to take the Boolean AND off, and an extra qubit, presumably initialized in state 0, which I want to copy the answer to, and then it returns all these. It returns the inputs unchanged and the extra qubit, the entangled one, that's the actual output. So that's the reversible version. And now the nice thing, one nice sort of high level operator that Quipper has is called classical to reversible. That's all that is. Classical to reversible is an operator that takes some classical thing like this. In general, it takes a function from A to circ B into a function from pairs of A's and B's to pairs of A's and B's. But what it does is it does the uncomputation of the garbage automatically. So now let's apply this to a list of 5 qubits and another single qubit, and then the circuit that I get is exactly what you would expect. So these 5 guys are the inputs. Let me label the inputs. How do I label the inputs? Let's not label the inputs, doesn't matter. The first 5 are the inputs. The next one is the output, right? I compute that thing, I copy it here, and then I uncompute the garbage. And that's the classical to reversible, that's not sort of automatically. So it's our first example of a high level operation on circuits, okay? Any questions up to here?
I have one tiny question. The Q naught instead of C naught, that's because it's...
Because I literally use C naught for classical knot and Q naught for quantum knot.
Okay.
So yeah, there's this convention that we usually use Q for quantum gates and C for classical gates. Okay. It's a completely arbitrary choice. Probably this would be, I usually even have to go to the Quipper documentation before I can remember what some particular gate was called. There's quite a bit of documentation though. The Quipper online documentation here. So yeah, if I'm looking for a gate, I usually go here, and there are all kinds of gates predefined, and I'm like, oh yeah, Q naught is what we call that thing. I think there is the one that's called C naught is on classical bits.
Gotcha.
So it's almost the same thing, but it's on a classical bit. You can't control it, for example, by a quantum bit, right? There's other kinds of some gates that we used. These ones are fairly common, right? Hadamard, X, Y, Z, whatever. There's also some swap gates, phase gates, multiple different rotations, with angles and time steps and whatever. Anyway, yep, so yeah, it's just a random name for that gate. Okay, maybe I can show you another thing. So classical to reversible is just a special case of when you want to uncompute some garbage. There's a more general thing that we often do, which is a lot of quantum circuits are of the form A times B times A inverse. You prepare some state, then you do some operation in the middle, and then you unprepare, all that stuff. And for this, Quipper also has a whole idiom, so maybe I can call this next function circuit 3. We want to input 2 qubits and output 2 qubits, and maybe what this one can do is input the Q and an R. And now I'm going to use this with computed paradigm. Let me just type it in and then I'll explain it. Maybe instead of code, I should call it something like preparation or something. And I would, for example, initialize an ancilla. So Q init Q, right? Because I'm initializing a quantum bit, not a classical bit. And some controlled gate. Okay, I don't know what these gates actually do. They're fairly random gates. Just want to make sure my program type checks. So the idea of with computed, maybe I can just draw this, right? You have some circuit inputs, and then you have some circuit A, and maybe it produces some garbage and some outputs, and then you want to do. So you have some operation B, maybe using more qubits, and finally you want to uncompute A, right? So maybe there's some intermediate state here that you just sort of carry through, right? So the classical to reversible would be a special case of this. So here we would just call this thing with computed A, B, right? A is the basis change or the preparation, and B is the thing that you want to do in the middle, okay? So my preparation here uses an ancilla. So there will actually be more qubits in the, in this part than in this part. And then because A inverse does everything in reverse, this will automatically be uncomputed. So let's try this. I should be able to use print simple since there's no parameters. And let's just preview circuit 3. Right, so here was this part is my preparation, and then I do something, and then I unprepare, and also the ancilla automatically gets sort of terminated. Now we're not guaranteeing in the programming language that this qubit will actually be reset to 0, right? It's quite easy to write a program that doesn't do that. For example, if the C0 was going the other way around. But that's up to the programmer, right? I mean, no programming language. It's basically an NP-complete problem to decide if this qubit is actually 0 or not, or maybe even worse than NP. Certainly it's NP hard, because you can't even decide it for classical circuits always. But, Quipper is not checking that, right? The programmer is just saying it as a hint, right? So the compiler can know not to error correct this qubit. So with computed is, and the nice thing is, now that you have this circuit, you could make another one that uses that one as a building block. As in fact, it's the whole point of defining a circuit as a function, right? I haven't actually shown an example of that yet, but let's say we make a circuit 4 with 3 inputs, and what it will do is maybe just apply circuit 3 to qubits Q and R, and then apply circuit 3 to qubits R and S, and maybe make that controlled by Q or something like that. So every function that you've defined, you can also use as a subroutine in another function, of course. And when you do that, well, let's see what that will look like. There's some kind of type error. Probably I have to say return QRS. One thing I do want to point out. So here is, right. Here is the first copy of circuit 3. So it's only operating on qubits Q and R. Of course, there's some ancilla that gets used. And then the second copy, this is the A, the B, and the A inverse, right? And you will notice that when I controlled this whole circuit, Quipper was smart enough to know that it actually only had to control the B part, right? When you have a circuit of this form, where was it? When you have a circuit of this form, ABA inverse, and you now want to put this in the context of some larger circuit and control the whole thing, only a fool would put controls on every gate, right? Often you even can't, because A might contain initializations and stuff that isn't even controllable. But of course, we know that it's completely sufficient to just control the middle gate. And if we had by hand written all the gates in A and then all the gates in B and all the gates in A inverse, there's no way that Quipper could know that it's only supposed to control the middle part. So because we use this with computed paradigm, it's sort of automatically being able to figure that out. So that's another advantage of using that rather than, you know, sort of inverting A by hand. Okay, does that make sense? So that's something that happened here. All right, now I want to show you some larger, or maybe well, there's other stuff I can show. We could, for example, one thing Quipper has is a simulator, which isn't surprising. Sometimes we do want to check, you know, especially, I mean, if I have a program with 1,000 qubits, I'm not going to be able to simulate it. But if it just has a few qubits, then I can do that. And we do have a simulation library. It's not very sophisticated. It's not the most sophisticated simulator that exists, but it's good for like checking the correctness of some very small circuits. So what I have to do is first I have to reload Quipper. Okay. Quipper.library. I can't remember if it's library or libraries. Libraries, okay. Some of the naming of this thing has changed. So to do any kind of simulation, I need to give myself a random number generator. So here I'm just asking for a random number generator from the operating system. And then what I can do is I'm going to run. I'll do this up here. Just like we have print generic, there's also run generic, and it inputs a source of randomness and a dummy argument that tells me which real number type I should use for the simulation. So instead of double, I could use float, or maybe some real number type with 100 digits accuracy or whatever, but we'll just use the built-in double type. The number 0 is actually useless. It's only using this type. And then we want to simulate, for example, circuit 3, circuit 4 maybe, and we have to give some initial input like false, true, false, just to say what these qubits are going to be initialized at. And then it's every time I run it, it gives exactly the same answer, because every time I ran it, I used exactly the same random number generator, and it's deterministic. So if I get a new one each time, then I get a new random answer each time. So and what this particular simulator does is it just measures the qubit at the end and just outputs the booleans. There's also some other simulators that would actually output the complex numbers, you know, the amplitudes or whatever. So that's something we can do. But now I really want to show you larger circuits. So let's go and find some of those. Where am I? I am lost. I just have to pull the example from my other machine. Sorry about that. Here it comes. Nope, it did not. Okay, I'll just go there by hand then. Here it is. Maybe I'll type make just for good measure. So this is some algorithm that we've already programmed. There's a bunch of algorithms that, you know, Quipper sort of comes with, just to illustrate how you do various different things. And this one is called the binary welded tree algorithm. It's from a paper by Childs and a few other people. Again, you know, more than 10 years ago. Basically, the idea of this algorithm is, let me see, can we show the tree? Let's show the graph. The idea is, it was one of the first algorithms where you could actually demonstrate a quantum advantage, in the sense that there was a problem that provably you couldn't do classically. And then, you know, and the quantum computer can solve it efficiently. And what the problem is you make a full binary tree of a certain height. That's this top tree here. And then you make a upside down copy of that tree down here. And when you have the 2 to the n vertices here and here, you basically just connect them by a random, you know, you have some random pairing of the vertices. So you end up with a graph where every vertex except the very top and the very bottom has degree 3. So locally, every vertex has 3 neighbors. They all look the same. And you want to do a random walk on this graph, and the graph is exponentially big, right? Because it's this binary tree of a certain depth n. And you're basically given the code of the input vertex, and your goal is to try to find this exit vertex. And you can do it by random graph on the tree. You can make it so the amplitudes cancel out in such a way that, you know, after O of n steps, you find the exit, and then you can prove that classically it's impossible. Basically, you're not given any information about the graph except the adjacency matrix. So you can query, given a vertex, you can ask, give me the codes for the neighbors, right? But you can't do any sort of global analysis of the tree, and in particular, you don't know, you know, how these numbers, you know, well, we just ordered the numbers from 0 to 127, but in general, they're just some random vertex labels. So this is what this algorithm does: walk around on this binary tree, and one thing I haven't mentioned, but most people, when they think of a quantum algorithm, they think of the clever part of the algorithm. Like when you think Shor's algorithm, you think, okay, quantum Fourier transform, right? Like, okay, I have some oracle for modular exponentiation, and then I need to find the period of the function. So I use the period finding algorithm, which is basically you prepare some state, you apply the oracle, and then you do the QFT, right? But when you look at Shor's algorithm, if you look at the gates, let's say the modular exponentiation oracle could be 10 million gates, and the Fourier transform at the end is like 100 gates, right? So when you actually program the algorithm, you realize most of the bulk of the circuits is all these different classical oracles that we have to perform, like classical operations on n-digit integers, you know, raised to some power, and everything reduced modulo n, and so on. So your typical quantum algorithm, your typical quantum circuit actually looks really boring, because a lot of the parts of it are just classical. There's a lot of Toffoli gates, right, in some algorithms. So this here is so the way this tree is organized is, it has we have colored the edges. So given a neighbor, we have one oracle to give the yellow. Given a vertex, we can ask for the yellow neighbor, the red neighbor, the green neighbor, or the blue neighbor, and somehow that's how this algorithm is organized. And what you see here is sort of one iteration of this. It's a quantum walk, so you're going to do the same step many, many times. but this is just one of the steps. And the circuit you see here is basically an oracle that computes the neighbor, like let's say the yellow neighbor of one color of one vertex in this graph. And then you do that. There's a lot of classical gates, classical, everything's classical. And let's make sure we don't miss the quantum part. Might have to zoom out a bit so we can actually see it. Classical. Oops, here's the quantum part. Here we do some kind of basis change, another kind of basis change, and then the actual interesting gate is a rotation, a Z rotation by the angle 0.017, okay, radians. And we have the angle with more precision, but right now, just for the purpose of printing the circuits, printing up to 3 digits, right? So that's in a sense the only proper quantum gate in the circuit up to this point. Maybe these W gates, I don't remember what they are. It's also some kind of basis change, but it may still be possibly, I can't remember if these W gates are classical or not. But then, here you have your quantum gate. And of course, when you translate that to a gate set like Clifford plus T, this one controlled rotation might turn into 1,000 gates, right? Because you have to approximate the angles somehow, up to epsilon. But it's just to show, in terms of the programming of the quantum circuit, you're spending most of your life programming these oracles, right? And here's the uncomputation, right? After that, you just have to uncompute everything that you've done from here to here. So you undo the basis change, you undo basically the color yellow, and then you get to the next part of the circuit. Maybe we can zoom out more. Well, we can zoom out a lot. Basically, there's 4 colors. So here's the first quantum part, and then you're done uncomputing that color, and you do the next color, and here's a quantum part, and then here's the next quantum part, and here's the next quantum part. You do it once for each of the 4 colors. So really what we need is, first of all, we need a good way to compute these oracles, to program the oracles, right? Because who wants to write these gates by hand, right? So this particular implementation of the binary welded tree actually uses an oracle that we programmed by hand. It's like a clever thing. We figured out, a good way to use these ancillas to get relatively few Toffoli gates, just to get to here. It's still kind of a lot of gates, but in the big scheme of things, it's not so bad. But we programmed different oracles just to see how that would work. So, for example, one feature that Quipper has, and I will show you. So the circuit that I just showed you, I think is called, maybe it's bwt.hs, and that's basically, that's the oracle. Like, it's a particular hand-coded thing, with all these different subroutines that we each coded by hand. So that's what you just saw. It's very boring to program classical oracles. So what Quipper has is this feature, which is really quite useful. What you actually want to do, you see in the research paper, it says, it is well known that such and such problem has a classical solution. Therefore, there exists a circuit of size O of whatever. It would be nice if you could just program it by programming the classical solution, and then the compiler would somehow automatically turn that into a circuit of size O of whatever. So this is exactly what this build circuit keyword does in Quipper. Maybe I can illustrate it in a smaller example first. So let's go back to our where the examples were. Maybe I'll start a new one. Example 2.hs, import Quipper. So here I want to program some classical function. We did the AND before, but we actually did that with quantum gates. Now, bool is just the type of booleans in Haskell, true and false. Where are my slides? Test Quipper example 2. So, oops. It's complaining that I wrote half a definition here. Oops. Okay, reload. So, the type of true is bool and the type of false is bool. So these are like the standard booleans in Haskell. And let's write some classical function. Take two booleans and then maybe you return A and B or not A. Okay, that's a boolean function. And if I apply this function to two booleans, I get some boolean, true, false. I can make a truth table for it. Okay, so that's just an example of a classical function. And then I want to what will happen is if I put the keyword build circuit in front of a definition like that, then it will still define the classical function, but it will also define internally a second function called template example1, which is basically that same function translated to a quantum circuit. Okay, so let's do example2 equals, and there's the unpack keyword that will slightly clean up that function. So unpack example1. Why is that not working? Unpack template example1. Sorry, the automatically generated name always starts with the word template. Okay, so now the type of example2 is exactly corresponds to the type of the original thing that I wrote with two changes. Bool got replaced by qubit, and instead of the ordinary function arrow, now I have the circuit arrow here. So example2 would be the automatically generated circuit that's generated from an actual classical program. And then I can, I should be able to print it. Print simple preview example2. And it's probably something not too clever, right? Here's the and then there's a not, and there's another or. And you do the or by using white dots and starting with a qubit that's initialized to 1. And then of course I can do, after that I can do other stuff like classical to reversible, but we've already seen that part. Something like this. So classical so let's look at that one. And it's just the same thing, but with the garbage uncomputed. But so you can do this not just for simple functions like and or and not, but basically for arbitrary classical programs. And the way that it works is for any kind of built-in operation like this and this or and this not here, you just have to predefine a built-in quantum circuit. For example, there's a circuit called template ampersand and a circuit called template not, and so on. And then Quipper will automatically, so for example, if you wanted to use a function on integers here or natural numbers, then you would just have to have some predefined library of quantum integers and maybe addition and subtraction and multiplication on them, or integers modulo p, right? And you would still use this exact same mechanism to generate the circuits. And that's what we've done here. So we took the description of the oracle and basically just wrote a classical function to it. And it's still some kind of mess. There's an adder and a majority function and a carry and something else because certain vertices are computed by adding numbers to other vertices. And there's a parent function and a child function, everything you need to define a tree. We even defined a classical data type of node here, which is something. And then you just sort of write the program in the, in the classical way and write build circuit in front of everything. And you can, because you have a classical program, you can test it quite extensively, like you would, or debug it like you would any other classical program. Here's another kind of Boolean function. And in the end, this goes on for a while, there's a notion of color, right? And in the end, you generate the actual oracle using just unpack and this template mechanism. And if you want to see so this is not the hand-tuned oracle, right? This is just, we write a classical program without using any sort of clever tricks. And then we get Quipper to, so let's see this oracle. So it's called template. And you will see it's much, much less optimized than the one that we wrote by hand, because the way the when you take classical code and you automatically transfer it to quantum code, basically for every operation that you do, there will be a new ancilla created. You could do a better method, right? But the baseline method is just this. Every time you do an AND, there's a new ancilla. Every time you do an OR, there's a new ancilla. And you can imagine what addition, looks like and so on. So you get this very, very large circuit with lots and lots of garbage. And that's the oracle. And then you uncompute it, most of it, except the output that you actually need. And then the quantum step is still the same as before. So you can see, there's a trade-off, right? We get a program that I would say uses 10 times more qubits, but on the other hand, it was far easier to program than doing that by hand, right? And then, once you have this, then you could, when you look at this, when you look at the circuit, you kind of want to pull your hair out because it really does like very obviously inefficient things. For example, initialize some qubit and then immediately, and then not even use it like these 2 zeros here, or initialize some qubit and then immediately AND that with another qubit. Like if you'd done that as a human, you would have, clearly been able to do it with fewer gates. So you want to take this automatically generated circuit, which is really like an operation by operation reflection of that classical program. And now you want to have another library for optimizing such a classical circuit. And when we do that, we do have such a library. So here it's called optimized. It's the next circuit is obtained by taking the automatically generated one and then running it through our optimization, suite, which is now on the same order of magnitude, I would say, as the handwritten circuit. It uses more ancillas still, but much less than the unoptimized program. And in terms of the number of operations, it's actually comparable to the handwritten one. So this is the sort of thing that I mean when I say high-level operations, right? We say we can construct a circuit by doing X, Y, and Z. You just have a combinator in the programming language for doing X, Y, and Z. Translate this classical program to a quantum circuit, and then maybe apply some optimization to at least get rid of the unreasonable gates, right? And of course, you could, and here this isn't even like state of the art, so I'm sure you could write a better optimizer for classical oracles, but I think this one is already quite impressive compared to doing nothing at all. Okay, so these are some of the things. Yeah, I have more stuff, but I don't know how much more time I have. I think we're getting near the end, eh?
Well,
we've already seen quite a bit.
This is a lot of stuff. I guess if you have one more thing to show us, and then we'll generally open it up to questions or comments or whatever, or summary, whatever you'd like to do.
I could. One thing just for this example that I haven't showed you, but that would probably be useful to see. So the circuit that we've generated here, I'm going back to the hand optimized one just for example. It's a lot of Toffoli gates, like I said, and then there's a controlled rotation, right? But of course, that's not how it's going to really run on the quantum computer. Our quantum computer probably has a gate set. It's probably Clifford plus T or Clifford plus T and a few other things, or it might even be something more low level like lattice surgery or whatever, depending which kind of surface code or error correction you use. So clearly before this logical circuit ever runs on a quantum computer, it should be translated to a more standard gate set. And this is also something Quipper has libraries for. Let me just go back to the help here. If I wanted to translate it to a particular gate base, for this program, I have the G option. So we could, for example, translate this same circuit to Clifford plus T. Now, it will take a lot longer to see it, but that's only because Acrobat Reader is quite slow. Quipper will generate the circuit almost instantaneously, but then you can see in Acrobat Reader it's got a lot bigger, right? I still haven't zoomed in. And what happens is, for example, every one of my Toffoli gates had some translation, into C NOT gates and T gates, right? So there's some kind of standard decomposition of Toffoli. And then let's get to the quantum part. Let's see if I can find it. Should be about 1/8 to the circuit. Here it is, right? This was still part of some classical basis change. And then I got, and you can see it in the comments here, he's like, enter approximate synthesis, blah, 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 for this angle theta, and which is a rational number, and some kind of epsilon. And all the gates that you see from here for the next bit of circuit is just a Clifford plus T decomposition of that particular rotation, up to some epsilon, which is, I think the epsilon is possibly configurable or maybe not. So that's another thing that we can of course do, translate to a gate set or another, and there's sort of various predefined ones, or you can define your own transformers. We can also do things like not just replace each gate by another gate or by another circuit. We can also do things like replacing each 1 qubit by 7 qubits or something like that, and replace each gate by a more complicated thing, like let's say for if you wanted to implement a Steam code or something like this. So we can still do this at the logical level. Although some of these things, it would probably be equally good to do it in some other tool. Like after you produce the circuit, maybe you want to have another tool in your compiler chain that would, optimize it for your particular hardware or whatever. So this particular gate translation is still at the level of logical circuits, which is not necessarily the best thing to do for every application, but it's another feature that is there. Okay, so maybe I'll just stop here and take questions.
Very nice. I have a couple questions, but I don't want to hog the question scene, so I'm gonna ask if anybody else in our Zoom meeting has questions and see what comes up.
Yep. Maybe I can't see the Zoom meeting while I'm still sharing my screen, so maybe I'll just stop sharing for a second.
Good idea.
Pause share. Oh, but where did Zoom go?
I noticed in some of the programs when you were running them, when you were executing them, you were typing in arguments that actually looked like code, like the replicate thing. So you can actually pass code as arguments in that mechanism.
Yes, like in any programming language, right? You can always pass expressions as arguments. Am I sharing? You're seeing my screen again, right? So in Haskell, replicate is just an operator that will make a list of length 5, filled with the number 7. So that works for any type. Like it doesn't have to be quantum or anything. I was just too lazy to qubit,
Yeah, no. So this is actually some sort of REPL that you're running inside of. Yeah. Okay.
Yeah, this is just Haskell. So the type of replicate is something like you take an integer and one element, and then you make a list of those elements.
But this is an interactive.
Yeah,
this is like IPython essentially.
Exactly. Like you can ask 1 + 1 and you get 2. So it's just an eval. Yeah, and I load the program, and then my print simple is an example of a function that Quipper defines. But of course, I can run it here in the shell. I could also, that's just basically for the talk, right? If you actually, often you have a compiled program like this. BWT was also a Quipper program, but I just compiled it. So yeah, you typically, if you want to compile it, you have to put a main function in, right? So main could be print simple preview example1. Now I should be able to compile it, example.hs, and then I get the linked program, and it does exactly the same thing. So yeah, the interactive thing is just better for while you're programming, you want to try out each function the second you've written it. I would still put the code in a file typically, right? Because otherwise you have to type it in over and over. But yep.
Another question regarding, you said that it keeps track of when qubits are not being used.
That's right.
And you had this situation where, you know, there's a big gap in the circuit time sequence.
Yeah.
But you just assume at the end of that sequence the state hasn't changed, or you, or and so another possibility is there are some architectures that support reinitialize.
Yeah.
Would that do the same thing instead of worrying about whether it's used? It's just,
Well,
in your circuit, just say, I want to execute the qubit operator that's, you know, reinitializes it back to zero.
yeah, it would be the same thing. So basically what we want is, because the programmer knows which qubits are ancillas and which ones aren't, and the programmer knows when we're starting and ending to use each ancilla, we want that information to be preserved in the circuit, having in mind that there will be other tools down the tool chain, you know, before we get from this logical circuit to some hardware. There would be other tools that would have to add the error correction and, you know, other stuff, gate sets and whatever. So it would be useful for those tools to have that information preserved, right, rather than trying to infer it from scratch. So the way we do it is just by annotating the circuit, not just when a ancilla is but also when the ancilla is terminated. Now you could also, you don't have to do that, right? You could just measure the ancilla or just leave it dangling, right? And then when you need to reuse it, you just reinitialize it to zero. But when you have an ancilla that's not being used for, you know, the next 200 milliseconds, it's useful information for the next stage of the compiler because it doesn't have to add error correction to that particular qubit, right? It's better, you know, if your computer has 100 qubits, maybe you're only using 30 of them, you know, there's no use in error correcting the other 70 that are currently idle, right? That's just basically the idea. And when we say it's in state 0, that's really just, that's not something we will check, right? It's just it's like a comment in the circuit, right? The programmer intended that this qubit should be 0 at this point. But
again, some architectures have an actual physical function that will reinitialize it. So
you could measure
able to?
You could measure.
Yeah.
And then when it's not 0, you just stop the whole program and say, you know, assertion failed. You could do that.
Yeah, I mean, you could measure it, but there's also, like on IBM, they have a specific command that says reinitialize it, whether you've measured it or not.
Sure.
So I'm just wondering if there's a hook in there to
to
just do it that way.
Sure, we could just have a gate called reinitialize.
Yeah,
we can have a gate. We can have a gate called anything. So, but I mean, this 0-0 sequence does the same thing, right? So when you see that and your architecture insert a reinitial, you could just ignore every time a qubit is terminated and insert a reinitialize every time it's reinitialized. Or if you wanted to do that in Quipper, you could just define a new gate.
From what I understand, doesn't reinitialize isn't it resource intensive compared with this?
Well, if there's a long time, if the time between when you stop using it and when you start using it again is long, then
no, I don't believe so, because I mean, I know that the IBM qubits, they brought it kind of late to the game. They didn't start out this way. They provided the capability to reinitialize a qubit after the fact. I don't believe it's resource intensive. It might take an extra millisecond over.
Oh no, I don't think the actual
reinitialization.
Yeah, I don't think the actual reinitialization takes any resources. It's just like, if you're done using this qubit and then you let it idle for a long time, and then you reinitialize it just before you want to use it as a new ancilla,
Yeah.
then something in your error correction is going to error correct this qubit the whole time, because you don't reinitialize it until the next time you want to use it, maybe. But I mean, you could
Okay.
when you
But I
finish
mean,
using it.
yeah, I think it'd be a known reinitialization, because I mean, from what you're saying is like you're just assuming that it will still be in state 0 when you get to that point.
No, we would
Why not just force it to 0 just to make sure?
Yeah, we would absolutely. This instruction absolutely forces the qubit to 0, right?
Okay.
Because we
Okay.
didn't
All
error
right.
correct it in the in-between time. So we must take a new qubit, right? So we're basically allocating a qubit somewhere, and that could be in some undefined state. So we initialize it. This is basically a reinitialized gate. The only difference is that we don't even think the qubit is part of the circuit while it's not being used. So next time you need an ancilla, you can just take one from a pool. It's not important that it's exactly the same qubit, that you used the last time. It could be some other subroutine has grabbed that ancilla and now you get a different one. It's just an annotation to make it easier to optimize the circuit after, right?
Yeah.
IBM has a different thing too.
Yeah. IBM has an actual function that does that. It's an actual microwave sequence to reinitialize it and whatever. But anyways, you have the ability to define registers of
absolutely.
collection of qubits.
Yep,
and
we do
deal with them as a register.
Let me show you an example. What's the best example? Let me see if I can find it. We implemented a quantum linear systems algorithm. And there we defined, let's see if this is it. We defined a quantum double type. Well, first of all, let's start with a quantum integer type, right? That's like basically an example of a register. So we define a quantum in some kind of signed integer. It's basically a bunch of bits which are like the digits of the integer, and this one I think is a sign, plus or minus. So just represented as a single bit. You could, implement integers in various different ways, but basically a register in this functional programming language is just a list of qubits, right? But here we interpret it as an integer, and then we define all kinds of functions on integers, like first there's stuff for padding and shifting, and then later there's like subtraction, multiplication, addition. So you define basically functions on the quantum integers, which are registers. Then we also have quantum double, which is even more interesting, because in this quantum linear system algorithms, you actually need a floating point, a quantum representation of a floating point number, and then act on that in superposition. So basically the quantum double is defined, I think we do it with fixed point arithmetic, so not floating point. So we do a signed integer and then some kind of exponent, okay, which is probably something times 2 to the minus n, and then we also have, this is all like in libraries, right? We have real functions. So for example, then we actually have sine and cosine and other like square root and other sort of real number functions, all implemented as quantum circuits here. And you can see the way it's been done is with this build circuit keyword. So we just implemented sine as a power series, actually. This is the power series. And then because we had already implemented multiplication and division and plus and minus, we could just write build circuit here now, and we automatically get, of course, very large classical circuits that do like this fixed point real number computation. So that would be an example. So it's very easy to define quantum data types in Quipper. You could either, they're user definable, or if you want something off the shelf, you just use something from a library, like these quantum doubles,
Very
which are
good.
probably misnamed because they're not really doubles, right? They're not any particular precision. They're actually fixed point numbers, but nevertheless.
So your build circuit, are you able to render that build circuit as just like an Oracle block or a,
Yep.
Yeah, cool.
There will be a function template approx sign that will be of type q double arrow q double, q double arrow circ q double, and then that will actually be the circuit, of course, that computes the sign function on this fixed point real number representation in the quantum circuit. It's huge, right? I mean, this is not going to be a small circuit. We didn't optimize it because, you know, I'm sure you could do slightly better than this huge circuit, but it's already a reasonable implementation of a power series. So, for example, we use repeated squaring to cover, which is already slightly better than, but not much.
But so when you go to draw the circuit, does that draw as just a black box on your circuit, or?
There's no. You would just, by default, you will get all the gates drawn.
You'll get all the gates. Okay.
But it's usually too large to preview it in Acrobat Reader like I've been doing. But you can output it in other formats, like just whatever. But we do also have a way to have, I didn't talk about this, but Quipper also has support for hierarchical circuits, where you basically just define once and for you, like you say, you can define a black box and say, this is a gate with 17 inputs and 17 outputs, and every time that's used in the circuit, it's just an abbreviation for this whole like sign function, right? And because you maybe define it once and use it a million times, and that's fine for resource estimates, right? Because if you just want to know how many gates, it would be silly to generate everything every time you use it, right? You just want to count the number of boxes and then multiply it by the cost of a single box. So we can do that, this thing that we call boxed circuits, I think. I don't see any example of that here. But if you actually wanted to know what this one circuit looks like, where did I go? Algorithms, what was it? Quantum linear systems, right? I'm even curious if we could just, should be Quipper I for the interactive thing. Can I print it? I'm curious now because it might just be too big for Acrobat Reader. So template. So just for computing. Oh, it's interesting. Okay, this was somehow. Okay, this is like a problem with Acrobat Reader. If you just get an empty.
Too big.
Here. No, it's empty. Probably. It's possible that I'm using. Yeah, because it's secretly a family of qubits actually, right? Because for our fixed precision real number computations, the precision is not actually fixed; it's a parameter. So maybe I should use print generic here with something, but I don't know. Yeah, we even need to know what a Q double is. Q double, oh god, it's an X double, and X double is some other thing. Yeah, it needs to get this in some extra integer argument. So yeah, sorry, I can't show you the circuit right now. It'll take me another 5 minutes to figure out how to show it. Never mind. But let's say if you wanted 100 digits of precision, that would be a very large circuit, obviously, for this power series.
Sure.
Do we have other questions? Peter, are you familiar with the programming languages that are big and popular now? And if so, do you have a preference?
I've seen some of them. I haven't used many of them. I think there's a number of toolkits that are based on Python, like Qiskit and whatever. And there's, I feel some of the better ones do many of the same things that Quipper does. So I like to flatter ourselves and say, maybe people learned something from Quipper and now they're doing similar things.
Frankly, I'm sort of amazed at the number of features that you have for a language that you developed 15 years ago.
Right.
It looks as if you've got everything going here.
Yeah.
But many of the concepts going that are just coming into Qiskit these days.
Yeah, some of the things I haven't seen often is this some equivalent to this build circuit thing, where you really just want to write the classical program and let the computer worry about, making the circuit. But I think some of I forget the names of the different toolkits and languages, but there are some that can do some analogous thing. Definitely. I don't know if Qiskit does. I haven't looked into that recently. It also probably keeps getting updated. So
we're getting some video from Heru, I think. Do you have a question, or are you just... Hello? No, I think the video is just coming.
Yeah.
I'm hearing something, but... All right, we're not able to hear you. If you'd like, type something into the chat. We'll see if we can address it. Otherwise, I think I'm going to turn off your video.
Let me see what happens. Oh, if I stop sharing, I can actually see you guys.
Hello? Hello.
Someone's question.
Yeah, I think we're having audio. I'm going to mute you also, just because I think if you have questions, please type them in the chat. In the meantime, we've been going for almost 2 hours.
Yeah, we've been going for long enough.
Indeed.
So,
hey, I mean, I'm going to come back on the screen just because I want to. And the other thing I want to do is really thank you so much for this. I'm impressed by Quipper. I'm impressed by the talk. I'm impressed by your typing ability. And I'm impressed by the voracious sound of your keyboard that seems to have kept me going for the last hour and 3/4. Peter, thank you so much for this talk. The next one, yeah.
I was going to say, when I was 16, I took a course at the time I was still using a mechanical typewriter. Okay, you can guess how old I am.
Yeah.
I was taking a course with actual secretaries and so on in typing. That was fun. And there were competitions where you had to type like 100 words a minute or whatever. So anyway, I'm very flattered that you commented on that.
I learned on a pharmacist's keyboard in the mid-60s. So yeah.
Good stuff.
Keep an eye, everyone, on the Chicago, Illinois, and beyond quantum meetup for our next talk. Please join us. Please, 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 please come to our talks, visit our website, subscribe, and we will see you again soon. Thank you.
And more importantly, if there's talks you want, or there's topics you're interested in, you can always post them. Send one of us organizers a message. Can't guarantee we can find anybody, but it's good to know what you guys out there want to learn about.
If you want to learn about it, we want to have a speaker about it. Within reason.
Awesome. Very nice. Thank you very much for the invitation and the opportunity, and see you next time.
Okay. Take care, everyone. Bye-bye.